Before we get into the control strategy, we need to consider how the motors behave. This is not going to turn into a mathematical exercise, but we do need a few expressions. If we apply a voltage across a resistor, a current will flow. So current equals voltage over resistance, I equals V over R. Similarly, we can say if an electrical current flows through a resistor, we can measure a voltage drop across it, V equals IR. We also need expressions for electrical power. Power P in watts equals V times I, which can also be expressed as P equals I squared R. Mechanically, power equals torque times rotational speed, or P equals T times S. We're now ready to consider the motor. The electric 9F uses direct current permanent magnet motors. The rotating part, called the rotor, contains coils, which as it rotates are connected in sequence by a commutator and spring-loaded carbon brushes to a DC supply voltage. The magnetic field that this produces acts against the permanent magnet field in the stator, that's the outer non-moving part, to produce a torque T. There's no inherent difference between a motor and a generator. If we spin the shaft of a motor, we generate a voltage. This diagram shows a motor connected to a voltage source. The motor still behaves internally as a generator, with a voltage Vg proportional to speed, and has a low voltage resistance Rm made up of rotor winding resistance plus brush resistance. It's convenient to consider Vg and Rm separately. It's important to realize that Vg plus Vrm is always equal to Vs. If we stall the motor by holding its shaft, Vg will be 0, and I equals Vs over Rm, which is a high current, so we will feel a high stall torque. If we then let go of the shaft, the motor will begin to rotate as its torque accelerates the motor inertia. As the motor speed increases, Vg will increase, and the voltage across the motor resistance, which is given by Vs minus Vg, will reduce. Hence, motor current will reduce. Motor torque depends on motor current, so torque will also reduce. Eventually, a steady state, no load speed will be reached, where motor torque balances motor friction. We will ignore the secondary effect of windage. Vg will have risen to a point where Vs minus Vg is producing just enough current through Rm to provide this torque. The motor characteristics are best visualized graphically. Unfortunately, FASCO provided no proper design data, so this graph is drawn from experience of similar motors. It may look complicated, but if we consider it one line at a time, it's really quite straightforward. The magenta line shows a linear relationship between current and torque. More current, more torque. With no load torque, there is a small current of 2.5 amps. The small value is what is required to balance motor friction at the no load speed, mostly brush friction. If we were to stall the motor, the current would rise to a very high value, shown here as 70 amps, and produce what is known as stall torque. In practice, my electronics doesn't allow the current to rise that far, since the motor could be partially demagnetized and would rapidly overheat. In between no load torque and stall torque, the diagram shows the linear relationship between current and torque. The blue line shows motor speed. If we begin to load the motor, we can see that the speed falls linearly from a no load value of 3000 rpm to 0 at stall. Any vertical line enables us to read off the torque, current and speed for that condition, but the red line is special. For this particular motor, we can see that it occurs around 25% stall torque, 20 amps and 2200 rpm. Any condition to the right of the line will result in the motor overheating. The heating doesn't just increase linearly with current, it increases greatly, because heating depends on I squared R. How soon a temperature would rise to a dangerous level would depend upon other factors: starting temperature, motor thermal inertia, cooling, etc. The red line defines the rated continuous running condition. For the motor shown, rated electrical input power occurs at 12 volts times 20 amps, that's 240 watts. Although we need a lot of torque for a loco to pull away from a standing start, we cannot allow that condition to last for very long, or the motor would burn out. The yellow line shows output power, torque times speed, but not to any particular scale. People are often surprised to see that maximum output power occurs at half stall torque. Rated output power also occurs on the red line. Motor efficiency, output over input, will determine how much less this will be than rated electrical power. I'm only a learner with LibreCAD and was unable to construct a typical efficiency curve. I've therefore shown it sketched here in green. We come now to the control strategy. In all these discussions we will consider that demand comes from a rotary potentiometer that sets an input voltage to the electronics. Firstly, we will consider the most basic system, where a single motor in a single loco receives a voltage Vs defined by the demand. We will make some initial assumptions. The loco pulls a heavy truck by means of a drawbar. The track is level. The weight of the loco is negligible compared to that of the truck. The friction of the loco is 0. The motor size and gear ratio are suitable. The term train covers the loco plus the truck. Kinetic friction is unaffected by velocity, and then we will not get hung up on the difference between mass and weight. Let us imagine that at rest we supply the motor with a modest voltage. This will cause a modest stall torque and force via the drawbar. The force will have to overcome static friction, but once underway only kinetic friction. Both will depend on the weight and the coefficient of friction, which will be less if the truck has ball races rather than plain bearings. As the truck begins to move, the motor back EMF Vg will start to increase towards Vs. So we will have to control Vs to keep it at a suitable level above Vg to ensure that Vrm, and hence Irm, provide an appropriate drawbar force to achieve the acceleration we require. Remember, force equals mass times acceleration. As we near our required speed, we can start to reduce Vs until the current, i.e. the torque, provided by Vs minus Vg, provides just enough drawbar force to balance the friction. Let's imagine now we come to an incline of, say, 1 in 100. The drawbar will have to supply an additional force of 1/100th the weight of the truck. That is, the component of weight due to the slope. If we keep Vs the same, the speed will drop until the new Vs minus Vg leaves enough Vrm voltage to cause the required current, i.e. the drawbar force, to balance the new situation. If we don't want the speed to drop, we would have to increase Vs a bit, so that Vs minus Vg provides an increased Vrm and hence Irm to supply the new total force required. Conversely, if we encountered a fairly steep decline and we didn't have a mechanical brake, the weight of the train could cause the speed to increase and Vg to rise above the demand, Vs. Vrm and hence Irm would reverse polarity. If Vs was simply a battery, the reverse current would cause regenerative braking, with the motor feeding energy back into the battery. If, on the other hand, Vs was being supplied by a lab power supply, the supply would probably be damaged, since the supply is not designed for this situation. In the case of specially designed electronics, it will depend on the design. Of course, downhill friction will help, and it will reduce the braking required. We can use regenerative braking at any time by simply lowering the demand Vs. More reduction, more braking. What about a single loco with more than one motor? No problem. Provided the gearing and wheel diameters are equal, the load will be shared equally between them. In a real system, the loco weight and friction will probably not be negligible compared to the values of the truck. Again, no problem. The values can just be lumped with those of the truck. What we have described so far is voltage control, where an increase in demand voltage results in an increase in speed. It's an inherently stable system, because if the train comes to a rise and the speed drops, Vg will drop and Vs minus Vg automatically demand more torque. The speed will drop, but only to a limited degree. Other possible control strategies, and the one decided upon for the electric 9F, are described in the next part.